Hi. So let's see. I think I'm recording. Am I recording? Yeah, I sure am. That's awesome. That'll be a good start to this video. I'm going to go through this bad Jimmy problem, and I'm going to specifically focus on parts B, C, and D. If you're watching this and you haven't seen part A, then I encourage you to work part A out for yourself. But I'm going to look at part B, C, and D. Let's get rolling on this. It says that this kid is at the top of a building that's 30 meters tall. He throws a ball straight up with a speed of 22 meters per second. And then focusing on part B, it says, what is the ball's velocity when it passes the kid on the way down? So that's what we're going to look at to start with. And we are going to try and see if we can draw. Cool. Okay. There's our kid. There's a ball, and up and down. Oops, and this again, okay. And there we go. And it of course continues to fall and hits the ground. But what we're going to worry about for right now is just what happens when it goes from right there to right there. Okay. All right, and we want to figure out the velocity of the ball when it passes back by him. So basically, what's its velocity right there? That's our goal. So we've got this drawn out. The next step that we want to do is to make a table. And so we'll make a table of displacement, initial velocity, final velocity, acceleration, and time. I could put y subscripts on all those guys except for displacement and time. But because of the fact that I'm drawing with my finger, I'm going to skip that. The initial velocity, if we look back at the last slide, it said that he threw it upwards at 22 meters per second. And let's see, the final velocity is what we're looking for. The acceleration is the acceleration due to gravity, which is negative 9.8 meters per second squared. Let's see, we don't know the time. And let's see, what about the displacement in the y direction? Well, it leaves his hand at a certain height, and we want to know what its speed is when it passes back by that height. So there's comparing the initial height and the final height to each other. The displacement is 0. Remember that displacement is final position minus initial position, and displacement and distance traveled are not the same thing. So its final position is the exact same as its initial position. So our displacement in the y direction, our change in height in the y direction is going to be 0 meters per second. Or 0 meters, excuse me. All right. So if I look at that, I can think about my kinematic equations and realize that this one right here will work really well. V squared is equal to V naught squared plus 2AY. Okay. Well, in the y direction, there's no displacement. That variable y there is 0. So when I plug in 0 for y, that entire term just goes away. And we are left with v squared is equal to v naught squared. And I'm going to go ahead and plug in numbers. Let's see, when I plug in 22 meters per second and square it, I get out 484 meters per second. And then when I take the square root, I get that v is equal to 22 meters per second. And that's great and all, but if I stopped right here and said that that was my answer, I would actually be incorrect because it's moving downwards. So I have to remember to put in that negative sign. And well, yeah, I can't just willy-nilly put in a negative sign wherever I want. There's got to be at least a little bit of justification for that. And where is that? Well, let's see. I took the square root of 484 right there. And we remember, if we think back that, let's see, a square root of a number can have positive and negative values. For instance, the square root of 4 is 2, or the square root of 4 is also -2. And it's up to us to make sure we pick the right sign when we take the square root of things. So that's our answer right there for part B. So let's take a look here. Part C says, how long will it take for the ball to hit the ground from when Jimmy threw it? So we're looking at the entire range of motion of the ball. And part D says, what is the ball's velocity when it strikes the ground? All right. So let's take a look at this. Switch back to black ink. There we go. I'm going to skip the figure this time, and we're going up and we're going down and we're hitting the ground, and right there. This is 30 meters. Okay. So, and I'm going to look at the entire motion of the ball. So I'm going to make my table with the starting point at the top of the building and with the ending point there on the ground. So that's why I put those asterisks in. So let's go ahead and make that table. My displacement is -30 meters. My initial velocity is 22 meters per second. My final velocity, I don't know that. My acceleration is -9.8 meters per second squared. And the time is, well, I don't know that either. So if I try to solve for time first here, and I look through my equations, the equation that actually will work for this is the following: y is equal to v naught t plus 1/2 at squared. So that'll work because, let's see, I've got the displacement, I've got that y value, it's -30. I've got the initial velocity, that's 22 meters per second, and I've got the acceleration, that's -9.8 meters per second squared. And so that leaves me with t as my only variable. So let's go ahead and plug those numbers in. I am going to do something I don't normally do. I'm going to drop my units just to make this a little bit cleaner looking. So -30 is equal to 22. Speaking of cleaner looking, I really wish that glitch on my computer would stop. Is equal to 22t. And then I've got plus 1/2 a t squared. Let's see, 1/2 of -9.8 is -4.9. Okay, let's move that -30 over to the other side. How do I do that? I add 30 to both sides. I get 0 is equal to 30 plus 22t minus 4.9 t squared. So this is, well, this is a quadratic equation. And, you know, we certainly can solve quadratic equations. Excuse me, we certainly can solve quadratics. How do we solve those? We solve those with the quadratic formula. Quadratic formula says that our values for t are going to be -b plus or minus the root of b squared minus 4ac over 2a. And that's great and all, but you know, if there's a way around this, I just would rather not. Yeah, it's easy to make mistakes in your calculator or what have you when you pull this guy out. So if there's a simple solution so that we didn't have to do this, I'd rather approach it that way. And the way to approach it then, actually, instead of solving for time first, is to solve for this final velocity first. And then once we have that value, we'll be able to solve for time. So let's do that. So I'm going to erase all this. There we go. And let's solve for that final velocity first. Let's see, how can we do this? Well, let's see, same equation as we used on the last slide. V squared is equal to v naught squared plus 2ay. So it looks like v squared is going to be equal to 22 meters per second squared plus twice negative 9.8 meters per second squared times my displacement of negative 30 meters. It's negative 30 because it ends up, the ball ends up lower than it was to start with. So it drops 30 meters, negative 30 meters. All right, so if I carry out the math on my calculator there and take the square root, I get a value of v is equal to 32.7 meters per second. And of course, I have to keep in mind, oh, I took a root. Let's see, is it the positive or the negative that I need? It would be the negative. This is negative 32.7 meters per second. It's moving at 32 meters per second when it strikes the ground, and it's moving in the downwards direction. And so that is my answer for that. All right, now that we've got that, which, hey, actually, that's the answer to part D of this problem. So that's checked off. Let's do part C. Right. And let's see, remake that table here again, at least attempt to. There we go. Y is negative 30 meters. Why is negative 30 meters? That sounds like a question. I don't know. Y is negative 30 meters. That's silly. Okay. Final velocity is negative 32.7 meters per second. Acceleration is negative 9.8 meters per second squared. And I'm looking for the time. And well, let's just do it over here. I can use any one of a number of different equations. Let's just use this one here. V is equal to V naught plus AT. V minus V naught is equal to AT. It looks like, let's see, divide both sides by A. We end up with T is equal to V minus V naught divided by A. And so as a result, we get T is equal to negative 32.7 meters per second minus 22 meters per second over negative 9.8 meters per second squared. And when we plug that into a calculator, we get out 5.6 seconds. And that is the result for that. All right. So let's take a look at this one real quick. It says what? We've got a pellet either shot upwards at 30 meters per second. That's choice A, or that's, excuse me, figure A. Or a pellet shot down at 30 meters per second. That's choice B. We're given, let's see, basically a multiple choice question. We're asked if the pellet in figure B strikes the ground with a smaller speed, a greater speed, or the same speed as the pellet in figure A. So think about that for a minute. You can pause this. All right, okay. So the answer is actually that they both hit it with the same speed. And this directly relates to our bad Jimmy problem that we just worked on. It said that Jimmy threw the ball up with a speed of 22 meters per second. And we figured out that, based on that information, when it struck the ground, that it was moving at 32.7 meters per second. That was the size of its velocity. The other thing we figured out, though, in part B of that problem was that when it passed back by him, it was moving downwards at a speed of 22 meters per second. Oh, okay. So whether, when it's at that height, whether it's moving upwards at a speed of 22 meters per second or downwards at a speed of 22 meters per second, either way, it's going to hit the ground at 32.7 meters per second. So it doesn't matter whether he threw it up or he threw it down. Either way, it's going to hit at the same speed as long as he threw it up or threw it down with the exact same strength. The last thing I want to address here is choice D. It says that the speed of the pellets when they strike the ground is 0 meters per second. That is never the right answer on these problems. that yes, after it strikes the ground, it's just laying there and not moving anymore, but that's really not interesting at all. When we ask what speed an object is moving when it hits the ground, we want to know what the speed is right at the moment of impact, not after impact. So don't make that mistake when you're going through and doing problems yourself. All right, that is it for this one.